Hi everybody, I thought we could do some integration by parts here, day 2, practice the stuff we've learned, and explore by parts in some new ways. So first problem I have to warm us up with, x squared sine 2x dx. We could do this with by parts twice, but I know that most of you would prefer tabular. So let's start with tabular, 2 and 0. Remember, every time we go backwards with this, not only do we need the antiderivative of the trig function, but there's going to be a 2 in the denominator here. So if we start with sine 2x and go backwards once, this becomes negative cosine 2x. But remember, when we take the derivative of this, there's no 2 out in front here, so there must be a 2 underneath. And every time we go backwards, another 2 is going to hop out. So this will be negative sine 2x over 4, and this will be positive cosine 2x over 8. Remember, we multiply on the diagonal, and so I end up here with negative x squared over 2 cosine 2x. Oh, hey, don't forget plus minus plus. So positive times negative, that's still negative, but positive times negative times negative is positive. 2 over 4 is 2. So I get plus x over 2 sine 2x. And then here, positive times positive, 2 over 8 is 1/4 cosine 2x. Don't forget the plus c, says Grant. Okay, problem 2, x to the third ln x dx. You know, this appears to be something I want to do with tabular, but isn't at all. Don't do this with tabular. This is by parts once. I know how to take the derivative of this, not the antiderivative. Maybe we should, think about that today. And so I'm putting ln of x here and 1 over x dx here. And that means that this has to be x to the third, which means the antiderivative is x to the fourth over 4. So when I integrate this, I'm going to have x to the fourth over 4 ln of x minus the integral x to the fourth over 4 times 1 over x dx. Well, I can do some canceling here and pull out this constant. So I'm going to have x to the fourth over 4 ln absolute x minus 1/4 integral x to the third dx, which will be x to the fourth over 4 ln x minus 1/4 times the antiderivative of x to the third is x to the fourth over 4 plus c. And yes, I would write x to the fourth over 4 ln x minus x to the fourth over 16 plus c. That would be my answer to this second problem, the integral of x to the third ln of x. Okay, 3. 3 is going to be a different kind of problem. Integral of inverse sine of x dx. Not derivative. I know what the derivative of this is, and you should too. Sounds like we should have a quiz on inverse trig derivatives. But for right now, we need the antiderivative, and I don't know the antiderivative of this. But since I do know the derivative of this, I'm going to do by parts. I'm going to put sine inverse x here, and its derivative, 1 over the square root of 1 minus x squared dx. But what goes here? Well, if all of this is my u, then what's my dv? Well, 1 dx. That's all that's left. So when I do the antiderivative of 1, I get x. And so now, when I follow my recipe for by parts, x sine inverse x minus the integral of x over square root 1 minus x squared dx. Now comes the question, how do I integrate this? Well, I see a function on inside and on the bottom. I see a function, and I see part of its derivative here. This is a u sub, where u equals 1 minus x squared. So du equals negative 2x dx. I have an x dx here, so I'm going to divide by negative 2 to get that x dx alone. Du over negative 2 equals x dx. So this can be replaced with du over negative 2. This can be replaced with u. So I can rewrite this as x inverse sine x minus the integral of 1 over square root of u du over negative 2. Well, I'm going to pull out this negative 1/2 to play with this negative out here, and I'm going to rewrite this with rational exponents. So I'm going to have x sine inverse x plus 1/2 integral u to the negative 1/2 du. Well, look, 1/2 u to the minus 1/2, that's the derivative of u to the 1/2. So x sine inverse x plus u to the 1/2 plus c. Check it out. If I take the derivative here, the 1/2 comes down, nice, and I subtract 1 from here. Perfect. Don't forget to sub back in your 1 minus x squared here. And so our final answer is x sine inverse x plus 1 minus x squared to the 1/2 plus c. Okay, so am I memorizing this? Yeah, I'm not memorizing this as the antiderivative of that. But it's good to know I can use by parts to help me find the antiderivative of that. I used by parts and then a u sub to help me get to my final answer. Makes for a great test question, doesn't it? Okay, let's take a look at this fourth problem. So we've got e to the x cosine x dx. Well, there's a problem here. When I do by parts, neither of these functions is going to go away like if I had a polynomial function for here. So I'm going to put my trig function here and my exponential function here. The reason being, I'd rather take derivatives of trig functions than antiderivatives of trig functions. The derivative of cosine, negative sine x dx. The antiderivative of e to the x is e to the x. So I know that the integral e to the x cosine x dx equals e to the x cosine x minus the integral negative sine x e to the x dx. Well, great. I can pull this negative out, this negative, and so I'm going to have the integral of e to the x cosine x dx equals e to the x cosine x, minus a minus is plus, the integral sine x e to the x dx. And you may be saying, well, Mr. Kukla, that looks remarkably similar to where we started. Yeah, but it isn't the same. It's just similar. So do by parts again. Again, put the trig function where you put it before, and the exponential function where you had it before. Otherwise, you'll just undo everything and end up where you started. So here we'll have e to the x as the antiderivative, and the derivative of sine is cosine x dx. Okay, so then my next step would be the integral of e to the x cosine x dx equals e to the x cosine x plus this times this, e to the x sine x, minus the integral of this times this, e to the x cosine x dx. Mr. Kukla, this isn't getting us anywhere. Oh, but yes it has. Behold, this is the same as this, with a minus in front. This is crucial. First, there has to be a minus the second time we do by parts. If there's not a minus here, we made an SIGN mistake somewhere along the way. Second, we want to keep doing by parts until we get back to where we started. Because, check it out, let's add this integral to both sides now. Plus the integral e to the x cosine x dx. Look, I have one of them, plus one more of them. That gives me two of these integrals equals e to the x cosine x plus e to the x sine x. So if I want to get this integral by itself, all I have to do is divide by 2. So the integral of e to the x cosine x dx is equal to 1/2. Ooh, I could even factor out that e to the x too. So e to the x over 2 cosine x plus sine x. Don't forget the plus c. So in problems where both of them are going to spin forever, I do by parts once, I do by parts twice, I should end up with a negative in front of my integral, so I can add this to the other side. Now there may be a coefficient here like 5/9, in which case I'm going to add 5/9 of that integral over here. 1 plus 5/9 would give me 1 5/9, or 14/9 down here. And so I would multiply by 9 over 14 on both sides. But the process is the same every time. Go and do by parts twice. When they look the same with a minus in front, add that to both sides, and then you're good to go. Okie doke. That's problem 4. Let's take a look at our next one. Integral of e to the 2x cosine x dx. So this is just a riff on the last one. I'm going to put my trig function up here. Negative sign is the derivative. E to the 2x dx, but remember, when I go backwards, it's not just e to the 2x, it's e to the 2x over 2. So now I get the integral of e to the 2x cosine x dx equals e to the 2x over 2 cosine x minus the integral e to the 2x over 2 times negative sine x dx. Negative times negative is positive, and I'm going to pull out that 2. So I'm going to have integral e to the 2x cosine x dx equals e to the 2x over 2 cosine x plus 1/2 e to the 2x sine x dx. Okay, I've done by parts once. I have a plus sign here. I'm okay with that. Let's do by parts a second time. This time we have sine x and cosine x on top. And down here, e to the 2x. Remember, when we go backwards, it's e to the 2x over 2. So now my integral will be e to the 2x cosine x dx equals e to the 2x over 2 cosine x plus 1/2 times this, e to the 2x over 2 sine x minus, don't forget that 1/2 now has to go here as well, minus 1/2 the integral of e to the 2x over 2 times cosine x dx. So I'm going to pull this 2 out, which is going to give me integral e to the 2x cosine x dx equals e to the 2x over 2 cosine x plus e to the 2x over 4 sine x minus 1/4 integral e to the 2x cosine x dx. So notice this is the same as my original. One of the reasons I write the original all the time here and write the whole line over and over is as a reminder to know when to stop and to facilitate adding 1/4 that integral to both sides. So if I add 1/4 to 1, I'm going to end up with 5/4 integral e to the 2x cosine x dx equals e to the 2x over 2 cosine x plus e to the 2x over 4 sine x and times 4/5. Don't forget the plus c. So integral e to the 2x cosine x dx equals, I'm going to distribute this and end up with 2/5 e to the 2x cosine x plus, these will cancel, 1/5 e to the 2x sine x plus c. So when both of them are going to spin forever, you go around twice with integration by parts. You should end up back where you started with a minus in front. Add that to both sides. Don't forget to multiply by the reciprocal, and you're good to be done. And Grant says don't forget the plus c. Okay, next problem. Yeah, I wanted to look at another tabular that had us needing to be careful going backwards. T squared 2t 2 0. But what about the antiderivatives here? E to the 5t is where we start. E to the 5t over 5. E to the 5t over 5 times 5. And finally, e to the 5t over 5 times 5 times 5, or 125. So I end up with t squared over 5 e to the 5t minus 2t over 25 e to the 5t plus 2 over 125 e to the 5t plus c. And I do say, when you practice these things, they do go faster. Okay, how about this one? Integral of z over e to the z dz. At first, this may appear as though it's a u sub, but I see a function, and I don't see the derivative of that function, nor, if I choose this for the function, is this the derivative of that function. So I think this is by parts, but I think I want to rewrite it so it says z times e to the negative z dz. So we've got z, we've got 1 dz, e to the negative z dz, and the antiderivative of that would be negative e to the negative z. So my antiderivative then will be this times this, negative z e to the minus z, minus the integral of this times this, negative e to the negative z dz. So what will that be? Well, minus times minus is plus. So we've got negative z e to the negative z plus the integral e to the negative z dz. Well, we've been doing the antiderivative of this a bunch. We know the antiderivative of this is negative e to the negative z. And we have negative z e to the negative z in front. There's my antiderivative for the integral of z over e to the z dz. Okay, next. Integral ln of x over x squared. You know, when I look at this, I again have that feeling like, well, I know the derivative of this is 1 over x, but here I have 1 over x squared. So dx, I could think of this as 1 over x squared, ln of x dx. Yeah, the derivative of this is not this. So what I'm going to do is say, well, let's make that x to the negative 2 ln of x dx. And we'll do by parts. I know the derivative of ln of x is 1 over x dx. And if I put x to the minus 2 here, the antiderivative of 1 over x squared is negative 1 over x. So this times this, negative ln of x over x minus the integral of this times this, negative 1 over x times 1 over x dx. So that's going to be negative ln x over x, minus a minus is plus, integral 1 over x squared dx. Well, that can be negative x over x plus the integral x to the minus 2 dx. And we did that a few minutes ago. We said that, sorry, let me catch up. We said that the antiderivative of x to the negative 2 was negative 1 over x. Don't forget the plus c. So we started off with by parts, putting ln as the u that we were going to take the derivative of, and dv was x to the minus 2. Then we followed our recipe. Here, behind the integral, we got negative 1 over x times 1 over x, which gave us 1 over x squared, whose antiderivative is negative 1 over x. Great. There's only a few more problems I'd like to look at. What about this one? The integral of tangent inverse of x dx. Not the derivative of tangent inverse, but the integral of tangent inverse. Well, this is by parts. I know how to do the derivative, so I put tangent inverse of x here, and 1 over x squared plus 1 dx here. What's left if all of this was my u? Well, I pretty much just have that dx, or 1 dx if you prefer. So the antiderivative will be x. So here, when I integrate, I'm going to have x tangent inverse x minus the integral x over x squared plus 1 dx. Ooh, look at that. That's a u sub. I see a function and its derivative. U equals x squared plus 1. Du equals 2x dx. So du over 2 equals x dx. Which means I can rewrite this integral as x tangent inverse x minus the integral of 1 over u times du over 2. So I'm going to pull out the 1/2, and I know this is going to be ln, so I've got x tan inverse x minus 1/2 ln of u plus c. And don't forget, our u was x squared plus 1. X tan inverse of x minus 1/2 ln x squared plus 1 plus c. Okay, so there's the antiderivative of inverse tangent. Again, I'm not memorizing this antiderivative, but I am realizing that I can find the antiderivative by doing a by parts problem. How about something similar but different? The integral of x tan inverse of x squared dx. Well, I see a function and its derivative. So the first thing I think to do is a u sub, where u equals x squared du equals 2x dx, or du over 2 equals x dx. So I can rewrite this x integral as tangent inverse of u times du over 2, or 1/2 integral tangent inverse of u du. Now I'm ready to do the last antiderivative that we did. Remember, we did that by parts. We put tangent inverse here, and the derivative, 1 over u squared plus 1 du down here. There wasn't anything but 1 du left over here, and the antiderivative of that would be u. So I end up with 1/2, please don't forget that 1/2, u tan inverse u minus the integral u over u squared plus 1 du. Now I need to do not a u sub, but a double u sub. U squared plus 1 is w. dw equals 2u du. dw over 2 equals u du. So I can replace my u du with dw over 2, and I can replace u squared plus 1 with w. So this becomes 1/2 u tan inverse u minus the integral 1 over w dw over 2. I'm going to pull out this 1/2 and recognize that this is ln. So I'm going to have 1/2 u tan inverse u minus 1/2 ln w. Now I have to distribute that 1/2. So I've got u over 2 tangent inverse u minus ln of w was u squared plus 1 over 4. 4 because 1/2 times 1/2 makes 1/4 plus c. And then finally, we had that other u sub back up at the top where we said u was equal to x squared. And so every place we see a u in this problem, we have to replace with an x squared. So I've got x squared over 2 tangent inverse of x squared minus 1/4 ln x squared squared plus 1 plus c. And so some people write that as x squared over 2 tangent inverse of x squared minus 1/4 ln x to the 4th plus 1 plus c. Wow, a double u substitution and by parts in the same problem. Does the love ever fade? Well, there's only one more new one that I'd like to do with you, and then I'd like to go through just some quick reminders of things that are commonly confused. Okay, so this one is a little tricky. Sine, not inverse sine, just sine, square root of x dx. Yes, so this is a u sub. It's not obviously a u sub, but it's a u sub where the u is the square root of x, or x to the 1/2. Now, I'm not going to take the derivative of both sides. First, I'm going to do something different. I'm going to square both sides. So when I square this, I get u squared, and when I square this, I get x. Now I'm going to take the derivative of both sides. So 2u du equals 1 dx. Well, here's a dx, which means I can replace that with 2u du. And here's the square root of x, and that can be replaced with u. So I can rewrite this integral as sine u times 2u du. Well, there's by parts. So I put my 2u up here, and I get 2 du. I put my sine u du here, and the antiderivative would be negative cosine u. And so now, when I integrate this times this, I get negative 2u cosine u minus the integral 2 times negative cosine u du. Negative times negative is positive, and I'm going to pull out that 2. Negative 2u cosine u plus 2 integral cosine u du. We know the antiderivative of cosine is sine, so we get negative 2u cosine u plus 2 sine u plus c. Are we done? No, no, no. Remember, we started off with x's. We know that u equals the square root of x. So wherever I see a u, I have to replace those u's with square roots of x. Remember, you can always check your antiderivative by taking the derivative. Okay. I have one or two more like that if you want them at some point. You won't see them on any test from me. They're not the sort of thing you see at the AP, but they do show up in college calc classes. And so, yeah, since most of you will be taking a second semester of calc along the way, you may well be experiencing those. Okay. So let's take a look at some familiar ones. 1 over y plus 1 dy. We should recognize this as a u sub where u equals y plus 1. So du equals dy. So I can rewrite this as the integral of 1 over u du, which is ln of u plus c. And since our u is y plus 1, and you may say, well, Mr. Google, I recognized back here that was an ln. Do I really have to do the u sub? Well, yeah, so the one thing I want to caution people about is often when they see things in the denominator, they say, that's going to be an ln. And sometimes it's an ln, and sometimes it's not an ln. Okay, so for example, y over y squared plus 1 dy. Again, this is a u sub. I see a function and part of the derivative of that function. So y squared plus 1 equals u. 2y dy equals du. So y dy is du over 2, which means that this integral can be written as 1 over u du over 2, which is 1/2 ln u plus c. And since our u is y squared plus 1, we can write 1/2 ln y squared plus 1 plus c. Okay, next. Integral of 1 over y squared plus 1 dy. Well, that's not ln. That's just inverse tangent. Inverse tangent of y plus c. And still, some people confuse not just these three with each other, but those with y plus 1 squared dy. This could be written as the integral of y plus 1 to the negative 2 dy. And I would do it as y plus 1 equals my u, so dy equals du. And so I'd be looking at u to the negative 2 du. Well, the antiderivative of that is negative 1 over u plus c. And now I plug back in my u, 1 over y plus 1, don't forget that negative, plus c. So those are 4 similar problems, and only 2 of them were ln's. Okay, how about this one? Everyone's favorite, 20 over y squared plus 25 dy. Well, we know this is something we want to be inverse tangent. We're going to divide by 25. We're going to multiply in the denominator by 25. I'm going to pull out these two constants, and I'm going to have 20 over 25 integral 1 over y squared over 25 plus 1 dy. We can rewrite this as 4/5 integral 1 over y over 5 being squared plus 1 dy. That's how I know that my u is y over 5 and du equals 1/5 dy, or 5 du equals dy. So I can replace my dy with 5 du, and I can replace this with u. That's going to give me this integral, 1 over u squared plus 1 times 5 du. Well, let's pull that 5 out, and then it can cancel with this 5. And so we're going to be looking at 4 times the integral 1 over u squared plus 1 du. Well, that's inverse tangent. 4 tangent inverse of u plus c. And our u, remember, was y over 5. So 4 tangent inverse y over 5 plus c is my answer here. Okay, last few that I want to do with you, more of the ones that people get confused. Integral secant squared x dx, that's just tangent x plus c, but the integral of 1 over secant squared x dx, that's a different matter. That's cosine squared x dx. And remember, when we have to do the antiderivative of cosine squared, yeah, I'm not doing by parts here. There is a by parts approach to this problem, and I hate it, where you put a cosine here and a cosine here. So instead of that, I'm using my power reducing identity. And I remember that cosine squared x equals 1 plus cosine 2x all over 2. Or if you prefer, well, no, just leave it like that. So this integral cosine squared x dx can become the integral of 1 plus cosine 2x over 2 dx. Well, I'm going to pull this out. That's why I said I wasn't going to split this into two fractions before. So I'm going to have 1/2 integral 1 plus cosine 2x dx. I like splitting this into two integrals at this point. 1/2 the integral of 1 dx plus 1/2 the integral cosine 2x dx. Because I'm going to do a u sub, and the u sub is for this part of the function. So u equals 2x, du over 2 equals x dx. I'm sorry, du over 2 equals dx. So my antiderivatives then, 1/2 the antiderivative of 1 is x, plus 1/2 the integral cosine u du over 2. I'm going to pull this 2 out to be with this 2, and I'm going to have 1/2 x plus 1/4 the integral of cosine u du. And I know that that's going to be the antiderivative of cosine is sine, 1/4 sine u plus c. And don't forget we said that u was 2x. So I'll finish this problem by doing my u sub, subbing my u back in, sine 2x plus c. Okay, let's take a look at two more. Integral of tangent squared x dx. This is going to be a trig substitution, secant squared minus 1. The antiderivative of secant squared minus the antiderivative of 1. Well, that's tan x minus x plus c. And finally, the integral of tan x dx. is the integral of sine x over cosine x dx. This was a u sub that we did, where u was cosine x. Negative du was sine x dx. And so we ended up being able to rewrite this as the integral 1 over u times negative du. So we got negative ln of u plus c. And since our u is cosine, we have negative ln cosine x plus c. Okay. Practice, 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 practice is what I can say about these mechanical problems. Hope this was helpful, and I'll see you all tomorrow or Thursday.